Let's now look at number 6 for this week's recitation. So what we have is for a fixed alphabet, sigma, we define a language that is semi-decidable or recognizable if there is a Turing machine M such that the language of this Turing machine is equal to the language we are looking at. So in other words, we have that for all strings inside the language, the Turing machine M is going to accept. And for all strings not in the language, we have M either rejects or it loops forever. So basically, like, it's different from what we have for decidable language in that for decidable language, we have a decider Turing machine in which we never loops. So for a decider Turing machine, if for all strings not in the language, we reject. And instead of like, we have like two cases in which we can either reject or loop forever. So what we want to show in this question is to show that L is decidable if and only if L and its complement are semi-decidable. So because it's if and only if, we show it in two directions. And the first direction is we prove that if L is decidable, then both L and L complement are semi-decidable. And so our assumption is going to be L decidable. And like just from the definition, we know that any decidable language is semi-decidable. So this will give us directly that L is semi-decidable. And also note that we know that decidable languages are close under complementation. In other words, if L is decidable, then L complement is also decidable. The way the argument here is that if we have L is decidable, then there exists a decider that whose language is equal to L. But like if we just like flip the accepting and rejecting state of that decider, it becomes a decider for L complement. So L complement is also decidable, and this implies that L complement is semi-decidable. Okay, so this is the first direction. And for the second direction, we assume that L and L complement are semi-decidable. And from the assumption, we know that there exists some Turing machine that recognize L and L complement. So say the Turing machine for L is M, the Turing machine for L complement is M prime. And we want to use M and M prime to construct or define a decider for L. So one way to one simple thought would be like, if N is the decider for L and we define it as taking an input string, say X, and one thought would be like, we first run mx. If it accepts, then we accept. And if it not, we run m prime x. And if it accepts, then we reject. So like, there is one small like thing with it that makes this algorithm doesn't work. And this is like about the definition of Turing machine that can recognize L. So note that it's possible for M or M prime to loop forever in the case that X does not belong to the language they recognize. So it's possible that if X is not in the language L, then in this case, if we run MX, then it's possible that it will loop forever, and this NX as a whole is going to loop forever, which makes it not a decider Turing machine, because we know that a decider Turing machine always stops. And so we have to find another way to define a decider for this. So this is kind of like a really common technique when we're trying to like define a decider Turing machine. This is like we define a new kind of like a new variable t, where t is in the natural number, and we simulate mx for t steps, and if it accepts, we accept. Also, like after we simulate m and we does not accept using m, we run m prime again for t steps. And in this case, if accept, we reject. So let's now try to walk through the code and see why this works. So remember that the previous algorithm doesn't work because it's possible for it to loop forever. Although like one thing we know for sure is that if x is in L, then m doesn't loop. And if x does not in L, then m prime does not loop. So this is pretty clear from the definition of the Turing machine that recognize L and L complement. So to take advantage of that, we know that if it does not loop, then it has to halt within a finite number of steps. Although like we have no idea what the number of what this finite number is, but if we loop through all the natural number, then at some point, say n, we're going to like reach this finite number in which either n or n prime stop. And by doing this, although like it may be like we're doing some repeated work because we simulate n and n prime for a lot of times, but it will prevent the whole Turing machine n from looping forever. Okay, so let's now prove the correctness of this Turing machine. So we have two cases to prove, and the first case is where x is in L. Then we know that x is going to be accepted by m because m is because m recognize L as we defined. And also know that we have to, in order to prove the correctness, we need to say that x is accepted by m with a finite number of steps. In other words, there exists some t in natural number such that mx accepts within t steps. And according to the algorithm, we know that if m accept, we accept. So this case we're good. And on the other hand, one thing to know here is we know that m prime never accept x if x is in L, because like m prime only accepts string that's in L complement. So if x is in L, we know that x is not in L complement. So M prime X never accept X. Okay, so on the other hand, if X is not in L, then similarly we know that there exists some T in natural numbers such that M prime of X accepts within T steps. Because M prime recognize L complement, and in the case in which X is in L complement, we know that it will terminate and it will not loop forever. So similarly, because X is not in L, MX never accept. So we're going to reject in this case, as we expected. So this proves the correctness of our algorithm, and we know that since a decider TM exists for L, L is decidable.